All right. I'm going to just stop the notes right here. You're not at the halfway point. It's May. Get in the game. You're in the home stretch. You just got 2 more units left. Awkwardly, one of those units is trigonometry, and it's like 3 units, but who's counting? It's only math. So perms and coms. This is a nice little dip of the toes into kind of number theory and how we can just use numbers instead of doing weird functions with them and without turning them into triangles, which is presumably what trigonometry is. I don't know. We haven't covered it yet. So I like this unit. It's kind of fun. It's also a little tricky. So we're going to go over 3 big ideas: permutations, combinations, and something called the binomial theorem. And amongst these big ideas, there are so many cool little applications, so many little ways we can test these skills. And it's really hard to say, okay, here's everything you need to know for permutations, because I could apply this sort of problem in so many different ways. So along with my video here, which is, I'm sure, going to be fantastic, I'm also going to post another video that has someone much smarter than I am also looking at permutations and also combinations and also the binomial theorem. But without further ado, let's talk about permutations. So in this video, we're going to cover 2 things: the fundamental counting principle. No, I lied. 3 things: factorial notation and general permutations and solving them. So let's start with the problem. Given a group of 5 students, how many different orders could we have the students line up in? In how many? Great sentence, me. Thank you. So let's make these students have names. So we'll call them Arthur, Barthur, Carthur, Darthur, and Arthur, or A, B, C, D, and E for short. And hey, look, here's my first way I could line it up. And then, okay, well, you can already guess there's quite a few ways that we could do this. Well, what if we just switched B and C, or C and D and E? Do we have tons and tons and tons of combinations which we could do this in? Before this, we've looked at sort of like tree diagrams on how we could do this sort of thing, and it's going to be a big tree. So let's kind of think outside the box. Let's consider, what if I have this idea? I've got a first position, a second position, a third position, a fourth position, and of course, the end of the line. How many different ways could I fill this first position? Well, there's 1, 2, 3, 4, 5 people. So I have 5 ways I could fill that position. Once I filled that position, how many people are left? Well, there's only 4 left. So if I want to fill the second spot, I only have 4 people to fill it. Then I only have 3 different people to fill it. And then the fourth spot has 2. And finally, the loser at the end, there's only 1 more person who can go in there. Okay, so if I have 5 different options for this, and then 4 different options for whatever's left over, then 3, then 2, then 1. Well, this is kind of an interesting sort of way of looking at it. If these are all different options, kind of like in probability, what we can do is we can multiply those different options together. And we're going to get a statement. 5 times 4 is 20, times 3 is 60, times 2 is 120, times 1 is still 120. We have 120 ways to do something. And this idea of taking these spots and filling them in has a name. And you probably guessed it. It's the fundamental counting principle. And that principle, or definition for right now, this is kind of not the perfect definition, but I don't care. You're in Math 30-1, not university. The principle states that if there are A ways to perform one task and B ways to perform a second task, then there are A times B ways to perform the combination of tasks. Cool. So that comes up a lot in trying to find out combinations of things. Now, with this, the order in which we're performing the tasks definitely matters, or has to be like separate, right? And so if we were just saying, pick 5 of these 5 kids, you've picked all 5 of them, right? Or make a group of 3 of these kids. The order doesn't matter. Then our kind of logic is going to change, right? So hold your horses on that one. But if our order matters, or if we're given sort of a combination of 2 discrete tasks where they're not interfering with each other, we can use the fundamental counting principle. So here's some examples. Mr. Herman, handsome guy he is, has 5 shirts and 3 pairs of pants. How many different outfit combinations does he have available? Well, if I have 5 shirts, that's sort of in task A, I have 5, and in task B, the number of pants, I have 3. 5 times 3, I have 15 different combinations. And if you don't believe me, what if I have shirts A, B, C, D, and E? Okay, so these are my 5 possible outcomes for shirt. What if I had pants 1, 2, and 3? Well, I've got 3 combos 5 times. There you go. That's our 15. 1, 2, 3. Right? So there's our kind of tree that we can draw now that it's not 120 branches long. It's still a pain in the butt. Let's use the fundamental counting principle instead. A certain place has license plates that start with 3 letters and end with 4 digits. How many possible combinations are there for license plates? And we will not assume that they're going to like censor it for like awkward combinations. So everything goes. We're in Canada where we're sorry, awkwardly. Let's pretend we're in America where we still ignore French people. No offense if you're French listening to this. Je apologize. But we're not going to have any like accents or anything. We just got a normal 26 characters in our alphabet. So if there's 26 letters and there are 10 digits, so that's 0 through 9, we have first 3 letters. So I've got 26 options here. And then it doesn't say the letters have to be different. So it's not like I'm losing a letter. So my second spot, I've got 26 as well. And then the third spot, there we go, I got 26 as well. So you could have something like, 1. Well, let's put the digits in too. So I got 10 digits, 10 digits, 10 digits, 10 digits for our spots there. So here's my license plate. 1, 2, 3, 4. There you go. That's a possible combo. How many possible combos are there though? Okay, well, I'm just going to type this in on a calculator. So I'm going to do 10 to the power 4 because that's what I see. And then I'm going to multiply that by 26 to the power 3. And that gives me a very unwieldy number of, hold on, do my decimals here, 175,760,000. Wowza. So let me write that down. 175,760, and then 3 more zeros for good measure. Cool. That's a lot of different license plates. You could have 175 million cars in that country and you would not be out of license plates. Wow. Let's do another. Let's keep doing more. Why stop? We're having so much fun. A group of students are forming a line. 4 of the students are nice, 3 of the students are awful. How many ways can they line up if, well, here we're applying a limitation. So let's do the one where we don't have a limitation first, actually. Let's go B first. If there's no limitation, the order does not matter in that, our order, that the lineup matters, right? But I'm not like facilitating a specific order. I've got 7 kids and there's going to be 7 options for first, then 6, 5, 4, 3, 2, 1. And so I can go ahead and I can just calculate that. Where am I? There we go. And that gives me 5,040 ways that we could line up. Wow, that's a lot of different ways we could line up. What if, though, I start applying limitations? And so this is a very classic kind of question where we're going to do limitations. And in this one, it says, no 2 awful kids can stand beside each other. All right, so we've got actually quite a few different ways this could go. But let's take a look at it one step at a time. All right, pardon me, water break. Okay, so with this question, like I was saying, there are a lot of different ways we could make this work out, but we're putting in some limitations. And particularly, there's a very spicy limitation here. No 2 awful kids can stand beside each other. And if I was a smart person making this question, I would have said, no awful kids can start or end the line, because then there's only one option for how they line up. But given this limitation, I've instead calculated that there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 different ways that they could line up. So let's take a look at the way I kind of meant to do it, which is saying if we end and begin with a nice person, the order in our middle has to be nice, or sorry, awful, nice, awful, nice, awful. So we get na 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 Batman. There we go with our order. So this is kind of what I was thinking. And let's calculate how that will pan out. So if I have this specific order, I have to have a nice person in first. And how many nice people do I have? I have 4. So there are 4 options here. And then this nice person, there's only 3 people left that are nice, then 2, and then only 1. Over here for awful people, blue being an awful color, there's 3 awful people that could fit in here, and then only 2 left here, and then 1 left there. Ah, interesting. Let's calculate for ourselves then using our fundamental counting principle how many different orders there are for this specific arrangement. Well, there's 4 times 9 is 36, times 2 is 72, times 2 is 144, which I guess, does that not make sense? Yeah, this is 12 times 12. Wow, look at me go. So 144 ways. Nito Spaghetto. All right. Now comes the hard part. What if I don't have the limitation that I have to start and end with a nice person? Well, it turns out there's a ton of different ways they can do it. I'm going to write these all down. I'm going to pause the video and write these all down so you don't have to watch me writing, and then we'll see. Maybe you'll be able to see if I missed any. All right, there's them all. I wrote them down, and I kid you not that so many times writing the letter N, I actually had to relearn how to write the letter N at these group of N's because it just started turning into nonsense. That's why I don't teach English. Too many N letters. I don't know. So I counted 10 different ways of doing this. I started with the cases where we started with A and ended in N. And then I did the cases where we started in A and ended in A. And then I did the cases where I started with N and ended with A. And I think that's all of them when you include our ending in N and N. So if I've got 144 ways to make each of these combinations, that means I have a total of 1,440 ways of doing no 2 awful kids can stand beside each other. Woof. Man, that'll teach you how to write your questions, Mr. Herman. Speaking of writing things, I hate writing all that stuff down, and I keep doing the same thing over and over again. I start with having like 4 people that could fit, then 3 people that could fit, then 2 people, then 1. And so I want to have a way that I can write that out effectively and sort of quickly. And I do have a way of doing that. And that's this whole thing that I probably have done this in class already, where I yell at you numbers and you guys all look at me like I'm an idiot, because maybe you're right. It's called factorial notation, and we use the exclamation point as a symbol. Aha, you get the joke now. And what factorial notation means that if I have n factorial, that means I'm going to take n and multiply it by all the numbers before it up to 1. And of course, when I say all the numbers before it, I mean all of the natural numbers before it. So don't throw any decimals at me, you jerks. So that's a really helpful concept when we deal with the fundamental counting principle, because we're going to end up doing a ton of that. My dog just ran into the room, licked my leg, and then ran away. So that was weird. Speaking of weird, we can do all kinds of things with our notation here. Let's start by doing some division. So what if I have 5 factorial divided by 3 factorial? Well, 5 factorial is 5 times 4 times 3 times 2 times 1, and it's divided by 3 times 2 times 1. So what am I left with? Well, I'm going to have the 3's cancel out, the 2's cancel out, and the 1 cancel out, and I end up with 5 times 4. That's 20. Okay, that's kind of cool, but maybe there's an easier way. What if we did this? 5 times 4 times 3 factorial divided by 3 factorial. That's a 3. Trust me. Hey, look, I can just cancel that stuff out. Obviously, I'm left with a 1 when I do all this canceling. I hope I don't need to tell you that at this point, but if I do, then there you go. So it's just 5 times 4, which is still 20. Good for us. That makes our life easier when we start working on stuff like this, because now I can say n factorial is n times n minus 1 times n minus 2 factorial, right? It's all the numbers after that, all the way to 1. Whatever n is, it goes all the way down to 1. So now I'm left with just n minus 2 factorial on bottom, and I have a case of n minus 2 factorial on the top, so they're going to cancel out. So I get n times n minus 1, which some psychos will write as n squared minus n. I'm not one, so there you go. Okay, different looking kind of question. This one's actually really going to use the same strategy, but we're going to end up with something that looks a little different. So n minus 1 factorial, now our numerator we know is smaller than our denominator because this is greater than n, this is less than n. So let's write n minus 1 factorial, brackets please, and then we'll divide it by n plus 3 times, got to go all the way down, n plus 2, n plus 1, n, and then finally we're at n minus 1, and we'll put n minus 1 factorial because we want all the numbers, natural numbers, between n minus 1 and 1. Hey, look, that cancels out. And like we said down here, we're left with 1. 1, that's a 1. And so we end up with this 1 over n plus 3 times n plus 2 times n plus 1 times n. And again, I'm not a psychopath, so I'm not going to actually expand that out. Sweet. So let's talk then about kind of what are we actually talking about? We're talking about permutations. We've used the fundamental counting principle. We know what factorial notation is. So what is a permutation? Hey, there we go. I wrote this down so you didn't have to watch me painfully do that. A permutation is an arrangement of items in which the order matters. So we've been doing permutations. Yay, good for us. Critical point. The most important idea here is that the order matters. It does not matter that I'm collecting students. It matters that I'm putting them in an ordered line where awful people can't touch each other or whatever it is awful people do. It's awkward now. So with this, order matters. It's a permutation. I'll let you guess what combinations are going to have to deal with. So let's talk about using permutations. We have a specific form of notation, which is NPR. And no, I'm not talking about the radio show. I'm talking about N pick R. N pick R, wherein N represents the number of options in this set being chosen from. So for example, there are 7 students from before, N would be 7. And R represents the number of options being chosen from the set. So let's say I have 7 students and I want to make a line out of 4 of them. I would have 7 pick 4. Now P kind of stands for permutation, but we say pick because 7 permutate R or 7 permutate 4 is just kind of like, I don't know, it hurts my head to say. So we have a formula that we can use for permutations, and that formula is that n pick R is equivalent to n factorial over n minus R factorial. Ooh. And so for this, we're going to definitely see cases where we have to do some algebra with this this formula of a permutation. And then we're also going to have cases where we're going to need to use this npick-r format. So follow along with me. Grab your TI-84 plus CE. If you don't have it handy, pause the video, go run to your math shrine in your bedroom and take from the altar the TI-84 that you have, or 83, old school, or like some freakish calculator that's more or less a computer. And hit the following buttons with me. We're going to hit math, then we're going to go over to the probability screen. And number 2 is npick-r. Now, if your calculator is a lot older, then you're just going to have that like NPR show up. You have to write a number before it, then type NPR, then a number after it. The number before is N, the number after it is R. For TI-84 plus CE folks, what we end up with is some boxes that we can fill in. So for example, if I did 7 pick 4 and I hit enter, which you guys could do as well, you'd find out that there are 840 ways that I can make an ordered line of 4 people when I'm given a group of 7 people. Spicy. Okay, so awkwardly, I just explained that without writing it down. So you're going to go to math, then you're going to go to probability, and then you can hit the number 2, and that gives us NPR, which will either show up as something like this, where you have to say 7 NPR 4, or you'll be nice and you'll get a little, oops, that's a P. I'm trying to draw. Oh my gosh, what have I done? Let's go back to where we were. If I really cared how these videos were, I'd edit that part out, but I don't, so I won't. Where is the button? There's the button. Okay. My calculator shows up as this. Oh, I almost drew an N again. Box and then P and then a box, and I can type the numbers in, and it's all good. So let's do some of that algebra we talked about. Yeah. Okay. So we're going to use factorial notation, which is kind of saying use the form that has factorial notation to solve 10 pick 7. All right, so we've got 10 pick 7, which means our sort of n value is 10, or r value is 7. And so we're going to solve it like this. We've got 10 factorial over 10 minus 7 factorial. Okay, and so what is that going to equal? Well, that's 10 factorial over, well, 10 minus 7 is 3 factorial. So what do we end up with? We've got 10 times 9 times 8 times 7 times 6 times 4 times 3 factorial over 3 factorial. Great. An alternative to this is that we could just solve this. You're saying, why would I have something nice and isolated like this and then break it down like this, you sicko? And I'd say, well, you probably don't know where the factorial button is on your calculator, unless you were paying attention when we said to find our NPR, you just go down 2 more. So math, probability, and instead of hitting 2, hit 4, and you get factorial notation. So I'm going to go ahead and do that. I'm going to go n factorial, and I hit the wrong button, so that's awkward, divided by 3 math factorial, and I get this number 604,800. And if I type this in, I've got, that's 10 times 9 times 8 times 7 times 6 times 4 times 5 as well as a number I totally forgot in there, sorry, times 5. And that gives me the same answer, to the great surprise of no one. Next question is, what is the value of n when n pick 4 is 360? Okay, well, let's go ahead and let's try this one out. If I've got 360, then that means that n factorial over n minus 4 factorial is equal to 360. Okay, so that's nice. Let's do some simplifying on this side here. So we've really got, and I'm going to kind of do it to the left. I know that's sort of gross, but whatever. N times n minus 1 times n minus 2 times n minus 3, which then is n minus 4 factorial. So n minus 4 factorial on the bottom cancels out for both of those. Sorry, I drew that a little regressively. And so I'm going to end up with this statement, which is that n times n minus 1 times n minus 2 times n minus 3 is equal to 360. Okay, so with this, I do have an option here of going ahead and doing something disgusting by expanding this and then trying to like solve out my equation. I could graph this, or I could use some logic here. So I'm going to take 360, I'm going to divide it by 5, then by 4, then by 3, then by 2. And hold on, let's see if that works out. and then I accidentally hit the wrong button. So I thought maybe n was 5, and I ended up getting something not quite right. So I tried again, and I said, well, what if n is 6? Then that will be 6 times 5 times 4 times 3. 6 times 5 is 30, times 4 is 120, times 3 is 360. Oh my gosh, I can't put exclamation points of excitement anymore because that means factorial. And so in this case, I find out, yay, I'm right. All right. Oh, sorry. I should write explicitly n equals 6. There you go. Happy now? Okay, show that 101 times 99 factorial is equal to 100 factorial plus 99 factorial. Ooh, what a cool question. So this question is from our textbook, and I think it's actually an example question. I'm going to take my textbook out and I'll find out. And yeah, I'm right. This is an example question from page 520. So I'll write this 520 in case you want to go look through questions kind of like this. Either way, let's show that 101 times 99 factorial is equal to 100 factorial plus 99 factorial. How do I prove this to be true? Well, what I notice is that I have 99 factorial as sort of like a singular term here, multiplying to something else. I can actually factor 99 factorial out of this guy as well. Watch what I can do. So I'm going to leave my left-hand side alone for right now. What I'm going to do here is say 100 factorial is like 100 times 99 factorial plus 99 factorial. Okay, well, now I can factor that 99 factorial out, and I'm left with 100 because that's factored out plus 1. Oh, hey, look, 99 factorial times 101. And so, cha-ching, they are the same. Left-hand side does equal right-hand side. Mwah! Very magnificent. Sorry, again, to the French people. All right. Now we're going to look at some more problems where we have limitations applied to permutations. Let's go for it. And then, oh my gosh, we're almost done permutations, right? No, sorry, this video is going to take about a year. Sorry to me, really. All right. How many different ways is it possible to choose a president, vice president, and a joker from a group of 8 people? All right. Well, with this, we have kind of no limits, really. It's not saying Jim can't be the Joker because he's already the president. You're just kind of going for free here. So we have our fundamental counting principle, but let's try doing that sort of permutation method here. So actually, we'll do both. We have 3 spots available. And really, it doesn't matter if we put vice president first or president first or Joker first. In any of these cases, I'm going to have 8 people to fill one of the roles, and then only 7 people left to fill the other, and then 6 people at the end. And so we're going to end up with 8 times 7 times 6, which is 336 ways we can fill those spots. Now, another way we could do that is we could say you have 8 people, and you need to pick 3 of them. So if we do our math all the way over to probability 2, we did 8 pick 3. Yeah, that also gives us 336. Cool. All right. How many different ways are there to rearrange the letters in the word Herman? Well, there are 6 letters, and there are 6 kind of spots we can put those letters in. So this is just going to end up being our fundamental counting principle where we say 6 factorial. And 6 factorial is 120 times 6, so it's 720. What I could have done is I could say, well, I want to take those 6 letters, and I'm picking all 6 of them to rearrange them. So I'm going to have 6 pick 6, which I'll go in, get my pick from it. And yeah, that gives me 720 as well. So there you go. And if I really wanted to, I could do this. Watch. I could say it's equal to 6 factorial over 6 minus 6 factorial. And then you'll say, whoa, Mr. Herman, you've got 0 factorial as your bottom. And you'll say, that's illegal. You can't divide by 0. Get ready for this. 0 factorial does not equal 0. It equals 1. What? Think about it this way. If I have 0 options that I'm picking from. I only have one choice, and that's to pick none of them. So 0 factorial gives me 1. Is that a satisfying answer? No, but kind of our math depends on 0 factorial equaling 1, so just don't worry about it. All right, how about if we have repeating objects? For example, for each of the following words, how many different combinations are there in order to rearrange the letters? Ooh, so Calgary notably has 2 A's. Good for them. So we have 1, 2, 3, 4, 5, 6, 7. And that means we kind of have like 7 factorial ways we could arrange those letters. But if I rearranged Calgary by just switching the 2 A's, I get the same word. So I haven't really changed anything. So what I'm going to do is I'm going to account for this by dividing away any instances of same letters and dividing it as a factorial. So if I have 7 factorial chances, 2 factorial of them can be factored out because they're just repeats. So I've got 7 factorial divided by 2 factorial, which is really just 5,040 divided by 2. I'm super impressed with myself for remembering that. I even think I did it right. Like, congrats, Mr. Herman. And so that gives me 2,520 different options for how to spell Calgary. Okay, well, Osoyoos is also a word with repeats, but it's got 2 different sets of repeats. So we've once again got 7 letters. So if we ignore for repeats, we got 7 factorial combinations possible. But now we've got 2 groups of repeats. So we'll treat them in 2 different groups. We've got 3 factorial for, never mind, there's 4 O's, good counting. 4 factorial to count for our O's, and 2 factorial to account for our S's. So I'm going to go ahead and I'm going to type this in. 7, oops, sorry, factorial. I'm saying sorry, but you can't even see what I'm saying sorry about. Divided by 2 factorial, which is 2, times 4 factorial, which is 24. And that gives me 105 different ways that I could rearrange the word Osoyoos. Neato. Okay, what if we had restrictions opposed on it as well? Back to Osoyoos. How many combinations of the word Osoyoos are there that start with an O? And then how many are there that start with an S? So we kind of got 2 questions in one. Good for us. By the way, if you don't know where Osoyoos is, it's somewhere in BC. It's one of the hottest places in Canada. So while we're getting our tan on over there, let's do kind of our number theory idea here, where we have our fundamental counting principle, where if I've got O must be in the first place, now I've got 1, 2, 3, 4, 5, 6 spots left. I've only got 6 letters, and so I've got 1 choice here. It's an O. Then I've got 6 factorial for the other letters. I've taken one of the O's, so there's 3 left now, and 2 S's still. So I'm going to have 6 factorial, which is 720, divided by 12, 6 times 2. And that says we have 60 different ways we could rearrange it if an O must be starting the word. Now, if we have an S starting our word, we still have that sort of 6 factorial left over. Now we have 4 factorial for the O's to account for all of them. For our 2 factorial, well, now it's 1 factorial, and that's, not very exciting. So we have 720 divided by 24, and that tells us there are only 30 combinations which we could do it in. Aw, less now. Okay, what if we have a class of 8 children, 4 of which identify as wearing red hats? How many identifies are there if the children can line up whichever way they want? Well, let's try our strategy of using n pick r. We'll do 8 pick 8. And so I'll go ahead and go math, follow with probability, hit 2, and I'll go 8, 8, and I get, wow, 40,320. That's a lot of different ways you could line up those kids. You could do that every day of school, and you'd run out of days in a year. Just barely. Okay, what if all the red hats have to stand together? Ooh. Now, keep in mind, just because they're all wearing the same hat doesn't mean they're the same person. So within our group, we're going to have to account for that. Ooh, interesting. Okay, so if all of our red hats stand together, then we're going to have, well, we've got a group of red hats. So we'll call this group R. And then how many are we going to have without red hats? Well, we've got 4 without it. So we've got a group of R that all has to be clumped together. And then there's 1, 2, 3, 4 other people or other spots, right? Now, keep in mind, this group of R is something that doesn't have to be in the first spot. It could be anywhere. And so really what we're saying is this is kind of like counting as one person. And then we've got the other 4 people. So we've got 5 factorial different ways we could arrange the people and the group. But keep in mind, this group of 4 people, we could arrange it in 4 factorial different ways, right? They could be in different places. So we have to take our 5 factorial and we have to multiply it by the fact that in each of those 5 factorial ways of lining up, there are different ways that that group can line up. Group was super accentuated there. So that's 120 times 24, which means we have 2,880 ways to have our group lined up. Okay, last question here. None of the red hats stand together is another one of those questions where accidentally I've made it really, really hard. I'm going to leave this as a bonus question for you if you want to do it. But one of the things we can think about is it might be easier for us to calculate the chances for them to stand together and then take that away from our total. So if I had written this question better and I said, it's illegal for all of the red hat folks to stand together. They have to have at least one of them separated, if not all of them separated, hopefully, right? In that case, what I should do is I should just take my total amount of options, and then I should divide away the 2,880, not divide away, but subtract away the number of options wherein I have them all standing together. All right. One last kind of question. How many paths can someone take from A to B if they only move forwards towards B from A? Ooh. Okay, how do we solve this guy? Well, what we're going to have to do is be clever in our work. I'm going to think about all the different ways that I could move. Well, I can only really move down and across, right? So I can go down and then I can go 1, 2, 3, 4, 5. Oh, sorry, I'm not even counting. I can go down and across. Down, I can go 4 down. So 1, 2, 3, 4 across and go 1, 2, 3, 4, 5, 6 across. So in total, I'm going to have 10 moves. And so there are 10 factorial ways I can do that in order. But remember, 4 of those are all down. So that is kind of like our Osoyus where there's repeating letters. It's now repeating downs. So I'm going to divide away that 4 factorial and that 6 factorial. And what I end up with then is a math statement I'm going to type in on my calculator. So I get 10 factorial divided by 720 times 24, which is I have 210 ways that I could get from A to B. Beautiful. It's important that you voice crack while you do this as much as possible. What if I have a weird little break here? Well, I'm going to break it into 2 different steps. I'm going to start by finding out how many different ways are there to get down here, and then I'll multiply it by how many different ways there are to get from here to here. Okay, so this is a square, a 4 by 4 square. So that means 4 and 4, that's 8 factorial divided by 4 factorial, 4 factorial. Down here, it's a 2 by 4 rectangle. So I've got 6 factorial divided by 2 factorial, 4 factorial. 8 factorial is 50, 40 times 8 divided by 24 and then divided by 24 again. So there's 70 ways to get through this box. And then over here, we've got 720 divided by 48, and that's 15. And then we'll multiply these 2 together. So 70 times 15 is equal to, sorry, this notation's hideous, whatever. So am I. 10 or 1,050 different ways in which you could go from A to B. Interesting. All right. One last idea with these kind of pathway questions is, yeah, don't throw away these questions quite yet. We might just come back to them. One other thing I can mention while we wrap up our video here is that I switch back and forth a lot between the ways I do the math. That's helpful. We know all our tools. We can use all our tools. And really, really helpful is being able to know some of these factorials. Like typing in the factorial symbol is surprisingly kind of like janky. It's not like our logarithm button where we can go just math alpha math, and it just pops up and we're happy. We do our little log dance. No, instead it turns out you have to like go through menus. So if you remember like 4 factorial is 24, you can do this question way quicker and this way quicker, and that helps. Do you need to memorize it? Absolutely not. Is it helpful? Maybe. Next video, we'll take a look at combinations. And until then, I'll see you later.